International Conference on Sustainable Engineering and Materials Development, ICSEMD 2021. As a participant of the 2021 International Conference on Sustainable Engineering and Materials Development, you are now part of a community poised towards contributing to a better tomorrow. This community consists of scientists, engineers, members of academic and research institutions, students, industry players across the globe, and organizers of this event that will be interacting on a 3-day virtual conference on sustainable engineering and materials development. Renowned professionals that will be gracing the occasion are ICSEMD 2021 is an incredible platform to network with top professionals in sustainable engineering and materials development. In preparation for this event, thorough peer review was done by the Technical Review Committee, and good decisions were arrived at accepting top papers based on scientific content and structure. In that regard, the organizing committee advises that you proceed with your registration and prepare for the conference held September 22 to 24, 2021. Kindly proceed to register for the conference and make your payment by creating an account or logging into your account on www.labingate.com. Click on the ICSEMD payment from your profile and generate an invoice. Further communications about the conference will be made available to all participants. Many thanks to ICSEMD 2021 partners, Labingate Incorporated, Canada, and Bells University of Technology, Nigeria, and exhibitors, CERC Malaysia, Centralized Analytical Laboratory, CAL, University Teknologi Petronas Malaysia, Planet 3R. We are looking forward to seeing you at the conference. Watch out for ICSEMD 2022.
I think we have a good professor is right here with us. And whilst we give her a bit of a time for her to catch her breath, I think that it will be honorable for Safa to reintroduce her, and so that we can fulfill all righteousness. But that is just a joke. Safa, continue.
Thank you, Dr. Desmond. Dr. Emily Chiang is an associate professor in the School of Engineering at the University of Guelph, Canada. Her expertise portfolio includes mineral carbon sequestration, waste valorization, and environmental remediation. Her work includes the formation of pedogenic carbonates in soils, the effects of soil amendment on plant growth and yield, the role of plants in soil weathering reactions, as well as phytoremediation of pesticide-contaminated soils and reduction of nitrous oxide emissions from agricultural soils. Please help me give a warm welcome to Dr. Emily Chiang, and we all thank you for your time and appreciate all the work you do. Thank you.
And the good professor will be talking today and engaging our intellectual abilities on the title of his speech, which is Enhanced Rock Weathering for Carbon Sequestration in Terrestrial Application. Prof, over to you.
Good morning, everyone. Can you hear me?
Good morning, Prof. Can hear you loud and clear.
All right, great. Sorry, I thought my presentation is at 9:20, so I was a little confused with the time over here. All right, so first let me just share my slide.
Please go ahead.
Do I have the ability to share the slide? Yes, I do. Okay, here we go.
Yes, we can see your slides, Prof.
Okay, awesome.
Excellent.
Okay. So thank you very much for the nice introduction. And everyone can see the full presentation view?
Yes, Prof.
Okay, awesome. Okay, so my name is Emily Chen. So I've been with the University of Guelph since 2014. And before that, I did my master's in University of Toronto. Then I worked for the mining industry for 5 years before I moved on to do my PhD. And I did my PhD in Belgium, in KU Leuven, there's quite a bit of a change, and that it was a result of me working in the mining industry and seeing a lot of environmental sort of hazard, after the mining activity. That's what sort of spiked me to do a PhD in environmental remediation, and hopefully is able to remediate some of the impact of human activity. Okay, and that brings to me the work that I'm currently doing right now in the enhanced rock weathering for carbon sequestration. Now, as you might know, University of Toronto, the University of Guelph is a university that is very strong in the agricultural research. So enhanced wet rockring in the application of agricultural activity is able to sequester carbon. So that is the research that I am currently working on. Now, as you can see, Paris Agreement, I'm pretty sure everyone have already heard about the Paris Climate Agreement. And this agreement is basically an international treaty on climate change. It was established in 2015 and was put in force in 2016. It was endorsed by 196 countries, and of course, as the name implies, it was set up in Paris. Now, what is the Paris Agreement trying to do is it is trying to limit global warming to well below 2 degrees, or preferably to 1.5 degrees before the pre-industrial levels. So that is the sort of a big picture that Paris Agreement has laid out. Because of this agreement and endorsement of many countries, a rapid transition to a low carbon economy is essential to avoid breaching of this agreement. However, unfortunately, this transition is insufficient to meet the mid-century net zero carbon emission commitment. And major economies, even though they are all committed to this, including UK, US, EU, China, Japan, that's not possible, for the even that we stop. Basically, the story is that even if we stop emitting today the CO2 or any greenhouse gas emissions, there's not much that we can do to bring down the temperature under the 1.5 degrees Celsius target. And based on the recent IPCC, the Intergovernmental Panel on Climate Change report, we know that meeting this target will require net zero carbon emission technologies. Okay. Although there are many carbon reduction emission technologies are available, and a lot of them are very effective in terms of reducing the carbon, there is no single carbon capture or sequestration solutions is able to limit the temperature rise alone. So basically what we're trying to do is that to come up with additional climate stabilization measures to complement the current mitigation approaches. So basically, so this is where the enhanced silicate rock weathering comes in. It can be deployed through agricultural land to evaluate for administrative atmospheric carbon dioxide removal, the CRD initiative. So what is ERW? It has a potential of co-benefit for improved food and soil security, and as well as reduce the ocean acidifications. Okay. And this is the work that I have been doing. So as you can see that the aim over here is to use the alkaline mineral mineral rocks to weather in the agricultural settings. There are many different kinds of alkaline silicate mineral that we can use in the work. The one that I'm working on is mainly the wollastonite. Of course, there are basalts, there are olivines that can be used for this application. But the reason that we use wollastonite as the main minerals for sequestration is because it has the highest carbon sequestration rate. And as well as at the same time, wollastonite is a known fertilizer. It can be organic certified too, so that it has many different kinds of applications. Because one of the key things that we're trying to promote over here is not just the carbon sequestration. We would want that this technology can be used by people that has a low entry requirement. So it's very easy to get into the market and with a very low market barrier to use this technology. Okay, so as we can see here, the picture, the SEM picture, this is what typical wollastonite look like. So it is a spiky needle-like shape. And what we do is we spread it on the ground, on the agricultural soil. Of course, not like that, but this is how it looks in reality. But we spread it. If you know about lime, how the farmers spread lime, it's pretty much the same way that we spread wollastonite in the field. In Europe, there are quite a bit of research on using the basalt or olivine and spread it on the land without agricultural activity. So just spreading the land. But what we're doing over here, we're using different plants and try to test what is the most effective plant or what is the most effective application rate in order to capture the carbon sequestration, capture the carbon. Okay. So now what exactly is enhanced weathering and what is sort of the chemistry that goes under behind the scene? I'm not gonna go through every single equations, and it'll be quite boring. But in general, enhanced rock weathering use our agricultural activity, and it has the potential to mitigate anthropogenic climate change. Now, as we can see over here, this is the first route for enhanced weathering is that the atmospheric CO2 needs to dissolve, right? So the CO2 dissolve and goes into the soil. The second step is that the wollastonite, the mineral that we're working at, needs to dissolve as well, right? So the first two reaction over here is looking at dissolution, right? So once they dissolved, they will produce bicarbonate and dissolved calcium. Okay, so that's the first step. Then what is it going to do is that the calcium is going to capture the bicarbonate and precipitate. Okay, so this is the reaction that we would like to induce so that we're able to capture that atmospheric CO2 and sequester it as calcium carbonate. And this is what we consider as a permanent sequestration. Okay, so that is slightly different than the organic carbon sequestration. This is what we call inorganic carbon sequestration because it is not related to organic particles. Okay, now there is another potential, so that the calcium does not bond with bicarbonate, but it's in the dissolved solution, and it will be carried by water and go eventually into the ocean. And in the ocean, because the pH of the ocean is much higher, so it will does the same thing as to capture the bicarbonate and precipitate as calcium carbonate. So that is another route. Basically, again, first we're going to have dissolution of the CO2 and dissolution of the wollastonite. Then we move on into precipitation of the calcium. Okay. Now in the plant. Oh, so sorry, I wanted to add one more thing here. So this is how the nature naturally capture the CO2. So for over millions and millions of years, this is how Earth captures the CO2. The problem with this process is that it is too slow, okay? And one of the main reasons is because the dissolution of calcium carbonate is a very slow process, right? So because of that, what, us as human that we're trying to capture CO2, what we were trying to do is to accelerate it, right? So to have a more intensified reactions, to speed up the natural, because through industrial revolution, we have emitted many CO2 into the air. And as we said, even if we stop, polluting today, we stop emitting any CO2 into the atmosphere today, we're not able to bring down the level of CO2 in the air. And so that's why we need to capture the CO2 in the air. Okay. So here again, with the agricultural activity, what we're trying to do is to use plants to help us to speed up the dissolution of wollastonite, or these kind of alkaline minerals. And why is the plant able to do that? As we can see over here, we have these plants with roots and with root nodules. And what these root nodules, they're basically little houses for bacteria, these rhizosphere bacteria, where the bacteria is doing its daily activity of releasing nutrients, absorbing nutrients, and releasing acid, polysaccharides, or different kind of components to aid the carbon cycle. Okay, and there are plants with root nodules and without root nodules. So if you have most of plants, they do their roots in their roots area, they will induce rhizosphere activities. But the plants with root nodules are the ones that our research has discovered that it does much better activity, because they have a lot more surface areas to induce these bacteria activities. Okay. So what we have over here, the atmospheric CO2, again, it will go through two routes. The typical routes is if you don't have the plants, right? You will have the rainwater, and the rainwater will bring the CO2 down in the soil, and it will induce bicarbonate, and the bicarbonate will react with dissolved calcium and form calcium carbonate. Right now, with the plants, we have additional, helpers to help us to release more protons. And with the protons, so these protons are generated by different acids that the bacteria secrete. Okay, so with these protons, it accelerates the dissolution of the wollastonite, right? So that we can have much more calcium. So as we have said, this, the dissolution of wollastonite, or the alkaline silicate minerals, are the reaction limiting steps, right? So that's why we would like to speed up this reaction, so that we can have more dissolved calcium to combine with the bicarbonate. Okay, so now here, instead of just the normal way, the normal route of the dissolution of CO2, we have additional and much more accelerated and faster secretion of acid to react with the wollastonite. And that is the benefit of having the wollastonite as an application in the soil amendment. Then here we're going to take a look at some of the results that we have obtained in the research. So this one, we're looking at using different kind of plants to capture CO2 over here. So we have the bean, as you can see over here, and the other one is the corn. Now, the reason that we have two pictures here is we were saying that on top of carbon sequestration, we wanted to make sure that whatever we're applying to the soil is helping the growth of the plant. So as you can see over here, for the bean, the one without wollastonite, just the normal soil, this is the height. And the one with the wollastonite is much bigger and much taller. And same thing that we observe in the corn study, that the corn without the wollastonite is smaller, while the corn with the application of wollastonite grow much bigger. Okay, and here we can see, so the result here is for soil carbon content, and we measured all the soil carbon content, the total carbon, the TC, the total organic carbon, the TOC, and as well as soil inorganic carbon. So as you can see over here, the highest concentration is the one with the wollastonite amended soil, right? So this one over here, almost in the middle too. So as we can see, the total carbon content of the wollastonite amended soil is much higher than the rest. Okay, and in particular is the increase of the total inorganic soil. So that is something that we have proven from a geochemical perspective, and as well as from the research perspective. Now, if we look at the research result for the corn results are not as significant. You do see an increase in the soil inorganic carbon, but not as significant as the bean, which is a plant that has root nodules, and that complies with our theory. And then we're looking at the calcium carbonate accumulation and the CO2 sequestration. So as we can see over here, the line here represents the calcium carbon sequestration. So as mentioned before, calcium carbon sequestration, calcium carbonate is a permanent sequestration of CO2 because it locks in the CO2. Okay, so this is the data without the plant. So there's nothing. There is only the soil with these wollastonite. Okay, as you can see over here, yes, you do have an increase, but the increase is very little. So again, this is how the nature normally captures CO2, right? So this is the natural process of capturing CO2 with addition of significant increase once we add the soybean. The reason that we stop over here, so these are the dosage. So we apply 1.5, 1.5%, 7.5%, 10%, 15%, and 20%. This is a dosage of the wollastonite in the soil. The reason that we stopped over here is because that we first, on top of CO2 capture, we also need to make sure that the plant grows well, right? If we're adding too much alkaline minerals in the soil, it will change the pH, and it create an environment that is not good for balance. Okay, so then we have the green bean. So green bean differs a little bit as 10% of the dosage. Then over here we have alfalfa. Alfalfa has a higher tolerance of the pH, so therefore we can move the experiment even further to capture more CO2 over here. But then eventually, the reason that it drops over here is because that the alfalfa did not grow well, right? So without growing well, it does not help with the dissolution of calcium carbonate. But alfalfa goes very well with the higher dosage of wollastonite. Over here, we can also see, as we mentioned, it's very important for the plant growth and the growth of the root mass, right? So if the root of the plant grows better, the plant itself grow taller and you will have more yield. So over here, you can see, so this is these pictures of the plant is corresponding with the percent of dosage of the mineral. So the first one over here is just soil. And then we have as the application of the wollastonite goes higher, and at this about 10%, you see the highest plant growth and as well as the root mass. You can see the density of the root mass over here is much higher than all the other plants. So that is another way that we prove that wollastonite is not only good for carbon sequestration, it is also at the correct dosage for different plants is able to promote the plant growth and root biomass. Right. So over here, we are showing some of the SEM and as well as SEM EDX pictures. So these figures shows the wollastonite as received and carbonated wollastonite. right? So if we take a closer look at the EDS spectrum of the carbonated wollastonite fragment, so these are the wollastonite fragment, and as we can see, the wollastonite is the, you see a lot of things over here because it is a different, there are a combination of wollastonite and deposite and different kind of mineral, but wollastonite is the main mineral in the combination. So these long needle-shaped spiky particles, they are the wollastonite over here. Okay, and if you see over here the concentration of different elements, that the main elements that is distributed inside wollastonite. So you have oxygen, which is the presence of oxides in the mineral. So we don't need to worry about the oxygen. But if we look at these three, silica, carbon, and calcium, right? So we see 21.3% of silica in wollastonite, and as well as about 24.5% of calcium. And the note that I wanted to bring you over here, you see 0% of carbon inside. Okay? As wollastonite as received does not have any carbon in it. Okay. Then we're going to look at the carbonated wollastonite that we received, or that we retrieved from our experiment. And then we did the spot sampling at 1, 2, 3, 4 different spots on the wollastonite peak. And if you look at the concentration over here, so again, the oxygen content doesn't change much, which is normal. And then if we look at the carbon, okay, so let's take a look at the carbon first, the blue line over the blue digits over here. So if we look at the carbon, you can see the carbon concentration increased significantly. Okay, so we're ranging from 16.7 to the highest of 22.4. Right, so this concentration increase compared to wollastonite with not carbonated, you can see there is a huge amount of carbon is being sequestered after it's in the soil through all of the agricultural activities. Okay, and the other thing that we observe over here is the amount of calcium has also decreased. Right, so you see the calcium over here is 24.5, but it's decreased significantly over here. And one of the reasons for the decrease, of course, as percentage-wise, because you have increase in the carbon, the calcium will definitely decrease. But also the reason is because the calcium is dissolved and leave the wollastonite. Okay, so that's one of the reasons as why the concentration over here changes. Now, because the dissolution of the calcium was bonded to the silica. So as you can see that the concentration of silica has also decreased, right? Now, there are many speculation as where the silica goes. One of the speculation is that, from our group is that the silica has dissolved and it, provided a way to entering the plant and travel in the plant and help the growth of the plant. So here we also look at some of the field study that we have done. The majority of our field study is done in the southwest of Ontario here in Canada. So we did the field study first in Paris. It's not Paris, it's Paris in Ontario, where we did the leafy vegetable field experiment. And over here, this is in Alliston. This is a potato field. And the last one is in Woodstock, which is a soybean field. So these are different types of plant that we wanted to see if in reality we have proved everything on the lab scale. So how do we see this in the reality? Okay, so in the field trial, we have a different layout. So this one in particular is the soybean, the field number 3, where we have different dosages. In the other fields, we have the same dosage for the field, but this one we wanted to see. We have 4 strips of different dosage and see how the things are. So this is the application, how the wollastonite is being spread on the soil, and this is how it looks like right after being spread on the soil. Okay, and here we have the soil analysis for the carbonate evidence. We use the calculation over here for the calculation of the carbon sequestration. So we have the result for field 1, which is the leafy vegetable, field 2, the potato field, and field number 3, the soybean field. So different field have different different results. Let me just we'll just go through this table. So for the leafy vegetable field, we have 3 years data for this field. So we have year 1, year 2, and year 3. And each year, as the year increases, the amount of application of wollastonite increases as well. Okay, so there are many data over here, but let's just take a look at the last one over here, the CO2 sequestered as the SiC, the solid inorganic carbon. So as you can see, the year 1 application results in 2.35 tons per acre of CO2 capture, and it increases by the year because the wollastonite application is more. Okay, so this one over here we have 4.17, and in year 3 we have 6.05. Because we can see the evidence is very solid, as we can see that the concentration of the CO2 capture goes up as the year goes up. The potato is the first year that wollastonite is being applied, and the experiment lasts about 5 months. Okay, and in this experiment, we witnessed 0.32% of tons CO2 being captured per hectares. And this is compared to 0 CO2 captured with the normal soil that has no wollastonite. And in the last field, we have about 20 weeks of data for this field. And this is the field that we have 4 strips of wollastonite, different concentration of wollastonite being applied, right? So it goes from 1.5 ton per acre all the way to 5 ton per acre. And also we have the control for the soil that has no wollastonite. And we can see from over here on the result that the one with the lowest concentration of dosage, we have 0.11, and it increases with the higher concentration of wollastonite dosage, and it goes to 0.4, which is the highest for the 5 tons per acre of wollastonite dosage. So as we can see that the evidence in our field work is the same as our lab research, that it shows that there is a very good capturing of the CO2 in the agricultural activity, agricultural land. Okay, so we have talked a lot about the the work. So hopefully it's interesting to you. So in conclusion, the potential for enhanced weathering of alkaline mineral in agricultural soil is huge. Through enhanced weathering, silicate minerals derive pathogenic carbonate, which is sequestering CO2 from the environment. And through this process happening in the soil, the origin of the CO2 is in the atmosphere. This is the atmospheric CO2. So the direct removal of CO2 responsible for climate change can be achieved. Mineral amendment of soil not only show increased soil inorganic accumulation, but also result in a better growth of the plant, which is very important, for the actual implementation of the technology. The co-benefit of these alkaline silicate minerals is CO2 sequestration, as well as improved crop yield, and this would really help the growers, the farmers, to adopt this work. All right, so that's the end of my presentation. Thank you very much. If we have some time, I can answer questions.
Thank you so much, Prof. For such an incisive presentation and for giving us a lot to ponder about. At least it shows that what we do in our labs and in our small cocoons are things that will actually shape the future of the world. And I think that we are doing well with time. And also on behalf of the organizing committee, I want to thank you so much for taking time off your busy schedule to share your wisdom, your experience, and your work with us. I think that it is really, really impressive, and we are really grateful. if we were to be in a face-to-face, we would have been clapping for you, but I know that virtually we've just clapped for you. I would use this opportunity to welcome some questions. We are doing well with time. So please, it's either you put your questions in the chat box or you just shoot your hand, and then we will then give you the platform to ask questions. It's time for asking questions. I always say that questions are like windows to greater instruction. So when somebody presents an idea, for instance, if you're to meet Prof. Chiang right now, and you want to ask her a question, what question would you have asked after this presentation? So please let us feel free. Remember, it is a conference. We talk, not just someone talking at you. So can we please, who want to go first? I think the good thing, you can unmute yourself and then you talk. Okay, Prof, whilst they wait to ask the questions, let me quickly ask mine. So in an event that, are you still open for taking students? And for instance, if you are open for taking students, what kind of students are you looking for? Or what kind of research, researchers or postdoctoral fellows are you looking for? Because this is really keen on my radar. Thank you.
Well, I think the most important thing, I think that when I recruit students, the most important thing to me is that if the students is interested in the work. I think interest is something very important because either you're doing a master's or you're doing a PhD. It is a long process if you don't like what you do. So, and also I think the other important thing is that the students needs to be curious about, asking questions and also trying to answer that question through research or through literature reviews, not just a Google search sort of thing. So yeah, I think curiosity and interest are very important characters. Yes.
Prof.
Yes.
Hello.
Hello.
Yeah, thank you. It's a very nice presentation. I think this is the first time I'm hearing about that particular compounds as a vital instrument for improving our agricultural crop, the agricultural material. So my question is that what is the difference between ordinary NPK fertilizer and this particular compound?
So you will still need to use the traditional fertilizers. So what these alkaline minerals, and the one that we're using over here is called wollastonite, is that it is a soil amendment. So you still use your traditional fertilizer to neutralize your field, but at the same time you can add in more of this wollastonite if you have, especially in the case where you have a pH problem.
Oh, thank you very much.
Thank you. Okay, so if there's no further questions, I thank you very much for inviting me for this talk, and good luck with the conference.
Thank you, Dr. Emily Chiang. We actually have one more question, and it's from Professor Ajayi that just asked if the participants have access to the presentation slides.
Sure, I can send the presentation in a PDF form to the organizer.
Awesome, great. Once again, we thank you so much for coming in and giving an awesome presentation. I think everyone learned a lot, especially me. I'm also in this field. I'm in environmental science, so it was awesome hearing more about this. Thank you so much.
Thank you.
Yes,